Hello and welcome to York Universe, the astronomy and astrophysics radio podcast, written and presented by the students, faculty, alumni, and friends of York University. You'll find us now wherever podcasts are distributed. I'll be one of your hosts this evening. My name is Julie Tomei, and I am joined by Dr. Mary Helen Armour. Hi, Mary Helen.
Hi, Julie.
We are broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night from 9 p.m. local Toronto time, that being 2 a.m. Universal Coordinated Time, on YouTube at York U Observatory, and in concert with our online public viewing program run by the Observatory team. To navigate to the show or find out more, check out our website at www.yorku.ca/science/observatory and follow the links to OPV for online public viewing. There you can join in the live chat on YouTube. For any questions or comments you have about our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on the socials, on Instagram with the handle at York U Observatory, or Facebook at Allan I Carswell Obs. All our programs are free, but if you'd like to make a donation, please visit our website, and we'll talk about that a little bit more soon. Again, that's www.yorku.ca/science/observatory. We'll be monitoring the chat room for questions to post content. The weather is cooperating this evening, so there will be live images from the telescope starting in a little under 15 minutes. Yeah. How are you, Mary Helen?
Oh, pretty good. So it's pretty clear out where I am. I was just out looking before I came in and could easily see Cassiopeia and Perseus. Oh no, the square. I always forget the name. I'm so bad with that. We're out and quite visible, even though it's not 100%. It wasn't 100% dark yet. So pretty clear skies tonight, at least where I am, just north of Toronto. So
Yeah, definitely. I was definitely noticing a big bright moon as I was going to pick up my daughter from work.
yeah,
All
it's
right.
fortunately still just rising, so anything more on the northern side was still fairly clear, and ski season hasn't started, so the ski hills near me haven't turned all their lights on, which is really annoying in winter.
Oh dear, yes.
Lots of light
Oh,
pollution. Can't
oh
get
yes,
away from
light
it.
pollution. I mean, the one thing that's encouraging about light pollution is that a lot of people now know about it. Um, I find that when I'm teaching like grade five, grade sixes, and I ask why do we not see a lot of stars from the city, at least one student, if not several, will be able to tell me why. So the awareness is going up.
Yeah.
All right. Shall we dive into our This Week in Space and Astronomy History?
Yes. So I think the first item up was one I had sort of dug up, and it's going back to the Apollo moon landings. Now, everybody remembers sort of the Apollo 11 and Neil Armstrong's famous words, but there was actually a second one that was ready to launch around the same time because NASA at that point doubled everything up, right? That's why there were two Voyagers, two Vikings, Pioneers that all kind of went around the same time. So Apollo 12 was actually on the pad to launch. But when Apollo 11 was successful, they delayed it, and it actually only ended up landing on the moon on November 19th of the same year, 1969. Um, and it actually landed near the old Surveyor probe. It was kind of a test to see how accurate they could place their landing. And it was funny because the first astronaut to descend, I'm forgetting his name now, was actually a bit of a shorter fellow, and he made a joke about, oh well, it may not have been a big step for Neil, but it was a much bigger step down for me. Um, so that was kind of his approach to stepping out onto the surface of the moon, which was a bit of a joke on Armstrong's, because a lot of people are like, well, how scripted was Armstrong's first words as he stepped out of the capsule? Like that was always one of the things. And he said he had a bet with a reporter, but that he'd say that, and he said he never got paid for the bet. So it was kind of those little bits of human interest story around this. But it was quite interesting because I everybody talks about the first moon landing. We talk about Apollo 11. Most people know about Apollo 13 because of the movie. The final landing was Apollo 17, but some of the other ones in between kind of get forgotten, and yet they provided just as much information to us, and had, detailed instrumentation packages that have, added to our understanding of the moon. And we kind of forget how many missions there actually were that landed on the surface in that sort of 2 or 2.5 year period between the first moon landing and the final one with Apollo 17. So Apollo 12 was actually the second one, and it was originally meant as the backup to 11 in case something went wrong there, but it turned out both of them were successful. So
Yeah, it isn't. It is interesting. You're right. Like we do hear a lot about 11, we hear a lot about 13, to a certain degree, less about 17, but it was the last
it
one.
was the last one. So people are at least, sort of familiar. But the other
Yeah.
ones like 12, 14, 15, 16 kind of get forgotten somewhere. And yet there were multiple moon landings. That's what sometimes people forget. So they always talk about, oh, the moon landings were faked. Apollo 11 never happened. As well, yeah, but there were also 5 other landings. So not like, come on, guys, what are they, fake all 6 of them? Yeah, I don't think so. So yeah, so it's quite interesting to read. And then when you think, like, we last landed on the moon in the early 1970s, and yet since then, nothing. It's when you think about like how long it's been
Mhm.
since the first landings in 1969, the two of them, it's sort of like it's kind of sad that we ended up stepping back and we're just now getting to the point where we're thinking about another lunar mission.
Yeah. Um, it's also, I mean, the further you go along those missions, right? They were like sending more and more stuff, right? They had buggies later, right? They were like
Oh
driving
yeah.
around, hitting golf balls. Like there was interesting stuff, both like on the sillier side of hitting golf balls and on the like scientific side of like being able to drive a certain distance and go a little further from the landing site.
Oh yeah, I mean it's incredible the technology they used and they had, and when you think about how the relative level of computer technology versus now, and they still managed to get there and land fairly accurately and take off again. It's just it kind of makes you sort of, it's sort of like, why did we give this up? Like, why is it more than 50 years now and we still haven't gone back, right?
Yeah. It's also
So
amazing how many missions in so short a period of time,
yeah,
right?
that they
Like,
managed to launch. I mean, then, and I can understand after that they went into a pause because it's a very expensive program, and there were all kinds of other things they had, to worry about, and they focused more after that on the space shuttle. But after the 1970s and the 1980s, it you had this huge burst in the 70s with the moon missions and the Voyagers and the Vikings, and then you hit the 1980s and there's almost nothing, right? Uh, because they just threw everything at the space shuttle instead. So it's interesting to sort of see some of the history of exploration. And it seems like after the moon ones, they lost interest in going beyond Earth orbit.
yeah. I imagine there was a little bit of a technology hurdle to get past.
Yeah, because I guess the next obvious step would have been a moon base, and they just weren't ready
Yeah,
to do that yet on any level. And to some extent, the whole moon thing was a bit about politics and the Cold War at the same time too.
absolutely. I
So
get the feeling it would not have gone nearly as quickly if it hadn't been, we gotta get there first.
gotta get there before the Russians.
Yeah.
But Yeah, and I think you had another a totally different sort of historical one
I
for your next
do.
item. So,
I do. So we're going back way back to November 9th, 1731. And this is the birth of Benjamin Banneker. And he was the first African American astronomer. He was also a naturalist, a mathematician, and an almanac author, as well as being a landowner. And as such, he worked as a surveyor and a farmer. So, thinking about the year that he was born, this is a big deal. So he was born in Baltimore County, Maryland, to a free African American mother named Mary Bannocky, and his father, who had been formerly enslaved. And his father's name was Robert, and who was from Guinea. He had little or no formal education and was largely self-taught. Like many Black folks at the time, not a whole lot of records were kept. And so, if you look into his family history, there are conflicting histories about the family. Um, but there are a few records existing. So he was named on the deed of the family's 100-acre farm in Pada- Patapsco Valley in rural Baltimore County in 1737. And there's a letter written by a Mr. James McHenry from 1791 that claims that his parents sent him to, quote, an obscure school where he learned reading, writing, and arithmetic, end quote. Around the age of 21, he reportedly borrowed a pocket watch from someone and then carved each piece to scale to make a clock that struck on the hour, which reportedly kept working until the year of his death. In 1772, brothers Andrew, John, and Joseph Ellicott, who were Quakers from Pennsylvania, moved near the Banneker's farm and got to know the family. And in 1788, Andrew Ellicott's son George lent Banneker books and equipment to begin a more formal study of astronomy. And during that following year, Banneker sent George his work calculating solar eclipse. In 1790, Banneker prepared an ephemeris for 1791, which he hoped would be placed within a published almanac. However, he wasn't able to find a printer that was willing to publish or distribute the work. Um, and in 1791, he assisted Major Andrew Ellicott, who was the son of Joseph Ellicott, in the survey that established the original borders of the District of Columbia, which is the federal capital district of the United States. His knowledge of astronomy helped him author a commercially successful series of almanacs. Um, and with help from the Ellicotts and connections to folks in the Quaker community, was able to start those publications, and they continued. He had correspondences with Thomas Jefferson on the topics of slavery and racial equality, and abolitionists and advocates for racial equality promoted and praised his works. Sadly, a lot of his papers and belongings were destroyed in a fire on the day of his funeral. But there is one journal that survives and a few artifacts. And the surviving journal contains a whole bunch of different things, math calculations, puzzles, a description of brood X cicadas and their 17-year cycle, and observations of hives and honeybees. He died in October of 1806 at age 74. And after his death, he became a folk hero. So many accounts around his life have been embellished or exaggerated. But there are parks, schools, streets named in his honor.
yeah, it's quite interesting when you look back how many of these historical characters um weren't recorded because of either gender or race or factors of that nature. So it's quite interesting that they can, go back and find at least something about some of these people who made contributions that we really don't know about or ended up being attributed to someone else in history, right? Um,
Yeah.
yeah, so
I was particularly excited about finding out about Benjamin Banneker because I didn't realize how early uh and I guess that's my own ignorance, right? How early uh the first African American astronomer came about. Um I mean, obviously he didn't go to university or anything like that, but his ephemerises, his almanacs were, the math was well done and people purchased them and he was able to make a career of it for himself.
yeah, like I said, if you think of the time and the place, it's really quite remarkable what he was able to accomplish.
Yeah, right. Despite the prejudice and racism and everything that he would have had to contend with just to get his work published.
Yeah.
Some of the quotes that I read were, ugh, they were like gut punches, right? It was like, despite his race, he's blah blah blah. Like, um, and he himself was like, in response to some of these, critiques of his work. It's like, why does my race have anything to do with this? Like, I did the calculations. They are right. The
What has it got to
end.
do with it? Yeah. So yes, it's like I said, in I looked at a couple of people sort of, I guess, historically too. Probably a name that most people who have looked at astronomy know, of course, is Edwin Hubble. Uh,
Hmm.
he was born November 20th, 1889, and of course he went on to become quite famous later on because of his discovery of expansion of the universe, right? Although I'm not sure he really called it that at the time. He looked at it more as all of the galaxies receding in the redshift, and it was later realized exactly what this sort of meant. So he was born November 20th, 1889. And I think you have some talk a little later about the Hubble constant. The other interesting one that sort of popped out at me from this week in astronomy history, of course, is uh, Albert Einstein. And one of the big early successes of his theory of general relativity was being able to explain why Mercury's orbit uh, goes beyond just being able to be calculated with Newtonian mechanics. And it was November 18, 1915 that he published that paper that explained Mercury's orbit. So you finally had an explanation of why you had this 43-second sort of deviation from the expected orbit, and they could never figure out prior to this exactly what was going on. And they speculated all kinds of things, including like another smaller planet inside of the orbit of Mercury that was disturbing Mercury's orbit. But this was one of the early sort of successful uses of general relativity in his theory, was figuring out the orbit of Mercury. So that was another really interesting one in that time period. I mean, most people think about general relativity and they think of Einstein, but they don't really understand like what general relativity was, like how did we prove it, and what could it explain? And this was one of the obvious ones. They also looked at, of course, the bending of sunlight from eclipses, but this was kind of one of the first early successes for his theories in this paper that he published. So
Did you see how many seconds the
it's a
orbit?
it's about a 43-second 43-second arc
Okay.
seconds, sort of arc seconds, sorry. I'd say arc seconds, bad. 43 arc second deviation in the orbit from the elliptical, so it ends up looking like a rosette instead of just a single ellipse, is because of general relativistic effects. So
Gotcha. I was
my
going to
bad.
marvel at how accurate they were at measuring the period of orbit.
No, arc seconds, not seconds. Yeah, my bad. Yeah, I tend to think of them interchangeably, but yeah,
I
they are.
mean,
I
fair.
should, yeah, and so I should be a little bit more
Oh,
careful.
good. The Yeah, Einstein's theory, so hard to prove, and yet it keeps being proved,
Yeah,
proven.
it's like I said, people thought he was a little crazy when he was publishing his theories, and yet over the last, more than a century now, time and time again, it has proved out, right?
Yeah,
So,
it's definitely an amazing mind.
so, and I think you had another physicist in the next one,
I
also a
do.
bit even related to some of Hubble's works.
Yeah. So we're going to November 11th, 1875, and this is the birth of Vesto Melvin Slipher, who is an astronomer that I had not heard of before this week, but did some important work. He was an American astronomer who performed the first measurements of radial velocities of galaxies. He was the first to discover that distant galaxies are redshifted. So therefore, those were some of the first empirical, or this was the first empirical basis for the expansion of the universe. And he was the first to relate redshift to velocity. So he was born in Mulberry, Indiana, and spent his years working on, or his early years, I should say, working on the family farm. He had a younger brother, Earl C. Slipher, who also became an astronomer later in life at Lowell Observatory, which is also where Vesto is going to end up. But we'll get there. He earned a bachelor's degree in mechanics and astronomy in June of 1901, and then followed that up with a master's degree and PhD in the same program, all from Indiana University. While he was at school, he formed a bond with his professor, William Cogshall, who convinced Percival Lowell to take Vesto on as a temporary assistant. And so he worked at the Lowell Observatory as an assistant from 1901 to 1915. That is a very long time to be temporary. When he was finally named assistant director of the observatory. And a year later, after Lowell died, Vesto became the acting director for the next decade. Again, a long time to be acting. Um, he was finally named director in 1926, and he stayed there until his retirement 28 years later. His research interests were in spectroscopy and redshifts, as mentioned, of what were then referred to as spiral nebulae, and we know them as galaxies today. But his first major task at the observatory was to measure the planet's rotation intervals. And he was the first to show that Uranus has a much faster rotation than Earth, similar to the other gas giants in our solar system. He also discovered absorption lines in planetary spectra for ammonia and methane and investigated the composition of planets' atmospheres. And his most famous work is with the galaxies. His first goal was to measure how fast they were moving, and his discoveries were confirmed a decade later at Mount Wilson Observatory by Edwin Hubble. In 1912, he observed the shift of spectral lines of galaxies, and then he used the Doppler effect to measure the speed at which they were traveling. And then this work led to his conclusion that these spiral nebulae were actually not part of our galaxy, the Milky Way, but out further. And in 1914, he also discovered that these spiral galaxies rotated. So by 1917, he'd measured a number of these redshifts, and he'd found that most galaxies, all but three that he had measurements for, were moving away from us at substantial speeds. Um, he also discovered, not related to galaxies, the sodium layer, which is a thin layer of neutral atoms of sodium within the Earth's mesosphere in 1929. And he hired Clyde Tombaugh and supervised the work that led to the discovery of Pluto in 1930. On the personal side of things, he and his wife Emma, who he married in 1904, had two children, David Clark and Marcia Francis. And he died at age 93 in Flagstaff, Arizona on November 8th, 1969.
Uh, Yeah, some of Slipher's early work was interesting. I mean, I did my master's on planetary nebula, and one of the things, the main thing I looked at was redshifts to see how you had the expansion of the nebula. So I was familiar a bit with Slipher and Hubble, not so much for um, some of the other work, but related to redshifts and galaxies. So yeah, Slipher was, like he was there before Hubble, but Hubble, for various reasons, got a lot of the attention and the name.
Hmm.
But Slipher, if you do any work on redshifts, he's known, but not the way Edwin Hubble is. He
Yes.
kind of lost out that way a little, I
Yeah.
guess.
He didn't get a fancy telescope named after him, that's for sure.
No. It's like one of those people, like anybody who works with that kind of stuff knows who he is, but beyond that, it's like many astronomers are slightly obscure unless you actually read into the kind of work they do. So,
Yeah, I don't know. It's interesting because like I I've not heard of him. I mean, I studied astronomy. We talked about redshift. He never came up.
yeah, it's because I think most of the credit gets taken by Hubble, but
Yeah.
when you actually start doing some research into redshifts and you read a little deeper, um, you realize with him it was more he was known for sort of the rotation of spiral galaxies because he only measured the velocity of a very few galaxies, and Hubble came along later and amassed a huge database
Hmm.
of them. So Slipher did a lot of the preliminary work, but Hubble was the one who sort of measured a lot of galaxies so that you could actually plot that graph.
Right.
Um, but Slipher did, especially with the rotation of spirals and proving they rotated and starting to look at how they were moving away. He sort of set the stage for Hubble to come along later and do a lot of his work. But again, some of it is just, I think, the time he's publishing in. If you're thinking 1914, 1917, you're right in the throes of World War One. So some of that stuff just kind of doesn't draw as much attention at the time, simply because there's so much else going on,
Yeah, it's fair. The world is fighting the war to end all wars, supposedly.
supposedly.
Um, yeah, it is interesting to think about, some of the things that are going on away from, the big, huge world-shaping events uh in areas that are important but not grabbing the attention because of the huge world-shaping events.
Yeah. And it's interesting. We forget a little bit how much. I mean, we tend to think in science about discoveries and stuff, but we forget how much the outside social context plays a role too. And I mean, I think that's one of the reasons, like, it's November. The Leonid meteor shower is reaching its peak right now. It was kind of the next point.
Hmm.
And what's interesting there is 1799 and 1833, there were spectacular Leonid meteor showers. And people are like, what is this? What is this? What is this? Um, and it was part of what led to an understanding of what meteor showers were. Um, I mean, the meteor linear shower comes from comet Tempel-Tuttle that comes back around roughly every 33 years. So it seeds the shower on a pretty regular basis. It doesn't always hit close enough to Earth's orbit to leave a really spectacular shower, but most years it does. So this shower was one of the early ones, along with a couple of other events in that time period, sort of late 1800s or late 1700s, early 1800s, those sort of few decades, where they finally realized that meteorites, yes, actually do hit Earth's atmosphere and do sort of crash down to Earth. So this is, I think, partly why the Leonid meteor shower fascinates me. It's also in November. If the skies are clear, you can usually see it really well, just because, less humidity in the winter. I always like looking at stars better in the winter because you can, as long as it's not cloudy, I find the skies tend to be a lot clearer just for the lack of humidity.
Mhm.
And if you look at the Leonid meteor shower, there are a couple of really sort of famous images of the 1799 and 1833 showers where people just show. In that era, it was drawings. This is before the camera. So, but you have these drawings where they're just showing dozens, if not hundreds, of shooting stars coming out of sort of the area of the constellation Leo. And it's really fascinating because at that time, they didn't know what meteorites or meteors were. Um, I know you mentioned Thomas Jefferson briefly earlier, talking to Benneker. I'm probably pronouncing his name wrong. But I mean, there's this sort of infamous, sort of urban legend type quote that, Jefferson at the time was saying it's easier to believe that two Yankee professors could lie than admit stones fall from the heavens. I mean, this this is their attitude from to meteors and meteor showers. And the Leonid meteors were one of those things that played a role in finally understanding sort of what meteors were, what meteorites were, the relationship to comets. This was kind of the starting point of this kind of astronomy. And being that I've done some work on asteroid impacts, I mean, all these little pieces kind of sort of fascinate me, right? That, this was sort of the turning point of understanding that, yes, things do fall out of the sky and hit Earth, whether it's meteor showers that, streak through. And then after this, they sort of came to in the 1800s. Oh, well, yeah, okay, smaller rocks fall to ground, and then later on, it became, okay, well, yes, big rocks do fall to the ground and you end up with the Barringer meteor crater. But it all kind of starts with, the Leonid meteor shower in that time period having a few really, really dramatic showers that got people's attention and started thinking about it. So this is kind of like, in the context of, I think, history, it's like you have this spectacular shower, and you have a couple of them within a few decades, and people start to really think about, well, what exactly is this? Because now you're in kind of this age of science where it's not like, okay, well, it's just, some unearthly phenomenon. What's the rational explanation for it? So that one always fascinates me, for not just because it's a really fascinating shower, but also because it's got this sort of interesting historical context of sort of some of the discoveries it eventually led to.
I have to say, I love looking at these depictions of like the 1833 one, these like lino cuts and wood cuts and like drawings.
Oh yeah, and it's fascinating because well, there's a lot of them from the US. Those are the most of the ones I'm familiar with, but it people really started recording things in this era, and you have more sort of interested science, sort of scientific approaches to things that I guess sort of started a lot of this. But it's like I said, the number of images from those sort of 1833 in particular, but there's some from 1899 or 1799 as well. It's just kind of fascinating that you have this shower that sort of generated so much artwork because you don't hear of some of the others in quite the same way. It's a bit interesting that way. And I even remember back in 1999, um, the last time it got quite spectacular. I mean, I think it was cloudy here in Toronto at the time, so you couldn't really see much, but they were showing pictures from around the globe of how spectacular this shower could be shortly after Temple Tuttle has passed, right? So maybe in another, oh, 8 or 9 years, if they're still doing the show, maybe they'll actually have some lovely pictures on the telescope of
Yeah,
all this, all these meteorites coming down. So if the weather
maybe.
cooperates, if the
Yeah.
weather cooperates.
It's
So
it's neat to I'm just scrolling through some pictures and it kind of like starts with like the drawings and the woodcuts and then it's like, oh, and here's a photo taken from space in 1997. It's nice to see like the year over year
yeah, like
progression.
and actually what and an interesting one is Soho because it's actually caught pictures of quite a number of comets as well. I mean, it's sun orbiting, but it's one of those ones they've used to track some of these comets to get a sense of where some of these showers might be coming from as well. So, but yeah, some of the it's like I said, the space pictures of these things coming in, it's like, holy geez. So you
Awesome.
just wonder how much of a threat something like this could be to modern satellites if you ever got a really intense shower again.
Yeah.
So
Um, I maybe not so good. But maybe we have too many satellites. I don't know. All right. So folks, you are listening to York Universe, broadcasting live from the Allan Carswell Observatory, located at York University in Toronto, Ontario, Canada. And we have just wrapped up talking about this week in space and astronomy history. We have one reminder this week, and that is that the observatory fundraiser is now on. So please head over to check that out at www.yorku.ca/science/observatory and click on the fundraiser link to bring you to the page. Uh, there's lots of exciting things that will happen with the funds raised. It will allow us to continue free tours, to create swag, to refurbish the 40 centimeter telescope, which is near and dear to my heart because it was installed in what is now the 1 meter dome when I was a student. Will allow repairs to the atrium, observing platform, refit of the 60 centimeter telescope, open research projects. There are a number of fundraising goals, and once we reach each of those goals, we will be adding stuff. Um, there are a couple of raffles. One for a free private tour for up to 6 people. And the other one, which is super exciting, is a supported viewing night. So the observatory staff will help you plan your observing session, and then you get to do some observing on the big shiny telescope. The last teletube of the month, this month, will be a special fundraising teletube. There will be at least 2 special guests to be confirmed soon. And there will be a new raffle held as every award tier is reached. So head over there, click the donate button, help us out. Okay. So let's talk a little bit more about the expansion of the universe. The James Webb, uh, it's funny how headlines are written sometimes. So the article I read about it said James Webb confirms Hubble's calculation of Hubble's constant. And it makes it sound like the guys, James Webb and Hubble, did these things, but it's the instruments that were used to do this, named after the guys. So both the Hubble Space Telescope and the James Webb Space Telescope have been used to derive the Hubble constant. And that is a constant relating the velocity of remote galaxies and their distances. So this new paper was by a team led by Adam G. Rice from Johns Hopkins University. And in it, they announced that JWST has validated the results of the previous HST study. So the Hubble constant, referred to by folks in circles of astronomy and physics as H naught, is a fundamental parameter in cosmology, and it defines the rate of expansion of the universe. It defines the relationship between Earth and distant galaxies by the velocity that they are receding from us. It was first proposed by Edwin Hubble in 1929 during his studies of spectra of distant galaxies. The units, for those interested, is kilometers per second per megaparsec. And it shows how fast galaxies are moving away from Earth per unit of distance. The exact value has been the subject of scientific debate. Recently, HST and JWST have been used to fine-tune that known value. And having an accurate value is key to finding or calculating the age and size and determining the fate of the universe. In their study, the team used JWST to look at the results from a study of Cepheid variable stars and type 1a supernovae as a distance ladder. So both these objects are standard candles. In other words, object whose actual brightness is well understood. So we know how bright they are at a given distance. So when you observe one and measure its brightness, you can then calculate how far away it is. And a number of attempts to measure H naught have been made over recent decades using various instruments and observations. Studies have resulted in a range of results, which has become known as the Hubble tension. And this study is attempting to like fine tune previous work and like kind of get it to like come to one value. It's difficult because of the sample size needed to have the precision that you want, and the number of Cepheid variables and supernova in that range. It is sort of the limiting factor right now. So the team also looked at other methods, such as a Hubble Space Telescope study of the luminosity of the brightest red giant branch stars in the galaxy, which is another standard candle, and another technique looking at the luminosity of certain carbon-rich stars. So taking all those techniques, putting their data together, the value that was found for this new study was 72.6 plus or minus 2 kilometers per second per megaparsec. And that compares to the value in the previous Hubble study of 72.8 kilometers per second per megaparsec. So a little bit more work is needed, but looks like we're honing in on a value.
Yeah, it's interesting, like how much work has gone into fine-tuning exactly what this is. But then the spanner in the works is this value actually a constant? Because there has been some suggestion that the rate at which the universe is expanding could actually be accelerating, right? And there's all that speculation about a sort of I guess inverse gravity, a repulsive force versus sort of the gravity that's the attractive force. And there's all this lovely speculation out there. So it'd be interesting to see if they could how accurate they can get it, and then see if they can actually see if there's any kind of acceleration actually happening, relative to sort of the relatively accurate values we have now. But it's like I said, it's finding the accurate galactic distances is the biggest catch in all this, because the redshifts will give you fairly accurate velocity values, but how do you know how far away the galaxy is in the first place? And it's trickier than people think, because most people don't think much when you say how far away it is, and but if you don't actually have a measuring stick of how far to go, and you don't have anything relative to look at, it's not the same as just here on Earth, right? Which is why you have so much time spent on Cepheid variables and type 1 supernova and various other approaches, because measuring distances is quite a trick in astronomy if you don't actually have some sort of more direct techniques, right? So.
Yes, that would be a very, very, very long measuring tape. Um, Whenever we start talking about distance measurements in astronomy, I'm always reminded of one day in class when Professor McCall said, "Distance is the Darth Vader of astronomy." Um, I've always thought that was very accurate. Um, yeah, I guess a lot of people, I mean, the distances in astronomy are so vast, right? So hard to wrap your brain around it when the everyday is like, yeah, I walk to school, it's a kilometer. I walk, I drive there, it's 100 kilometers. The odometer tells me, not, or is that the right word? Yeah, I think so.
Yeah.
It tells me how far I've gone, or I could use a trundle wheel or whatever, right? Like, they're astronomers have to get very creative about their trundle wheels.
Yeah, I mean it's fascinating when you go back over history. Like, the whole point of the Cepheid variable was, when it was being studied, was to actually create that standard candle, because finding distances, we knew they were far away. You just didn't know how far away until you could get some of this done. And even within our old solar system, finding distances to other planets was also tricky. I mean, Venus, it took a couple of the when it actually passed in front of the sun to be able to measure the accurate distance to Venus. And you had uh, astronomers at the time traveling all over the planet to be able to see that Venus pass in front of the sun. And this is part of how they figured out how far away it was, because otherwise it's not a simple proposition to try and figure out, because you can't just measure it directly. Right? This is sort of, I think this is one aspect of science people kind of miss a lot, and particularly I think in astronomy and some of the geophysical sciences, is, oh, there's a lot of things you can't measure directly. So we have to be very, very clever about how we figure these things out. Right? It's part of what the JS the James Webb and the Hubble telescope was about. It was all about finding ways to measure in distances and making that accurate. They're not actually measuring the Hubble constant directly. They're trying to measure both the brightness of these objects, um, and very accurate redshifts is really what they're after, to calculate the Hubble constant from. I mean, this gets missed sometimes, but yeah, it's kind of fascinating how that happens.
Yeah. Um, the other thing that's really interesting is that as we get more powerful instruments, will that help us? Right? Because, you know, okay, so we've got some Cepheids nearby and we understand them, and but when you're looking in another galaxy, you need to be able to have the observing power to it not just be a fuzzy blob.
Yeah. Well, that was the point of using the supernova. They're so bright, that you can use them to calibrate to galaxies. I mean, I still sometimes, like wonder what exactly was Hubble looking at sometimes when he was calculating these distances to come up with an idea for his constant, but they were quite loose at the time. But I mean, in astronomy, we get used to error factors that are quite large because we just know there are these limitations. Mhm.
It's within two errors or two
It's within an order of magnitude. It's
that's it. That's what I was like, the things of magnitude. It's with an order of magnitude. It's fine.
close enough.
I've also approximated a horse to be a sphere. Don't mind me. Um,
I don't know, this is something, I guess these are aspects of astronomy that if you're just an amateur observer, it doesn't quite click in until you actually start doing the math and looking at it and going, oh my God, there are like huge errors in this. And I've taught the history of astronomy course at York. I designed it years ago. And this is one of the sort of themes that keeps popping up is like how many things when people talk about astronomy, they don't understand all the sort of assumptions behind it and how hard it is to find these standard candles and therefore find distances. I mean, most students don't even think about it. You say, okay, well, like Venus is so far away. And then I ask them, okay, well, how did they measure that? How would they figure that out? And a lot of them get this blank look in their eyes and say, well, we can't run out there with a tape measure. What do we do? So it gets them really thinking.
yeah,
So,
yeah. I've been reminded of it frequently lately because I've been training up a bunch of colleagues on astronomy, and they ask fascinating questions. And I'm like, well, for historical reasons, this thing and the other thing. It's population one and population two. You would think population one is the older one, but they're not.
no. That's a problem when you're observing and you're attaching a name to something without really understanding it, right? And you get a lot of those. You get a lot of those situations in science, which can be very confusing to someone who's just learning it until they kind of understand what's actually happening, right?
And then the quirks that are just special to astronomy, like, so tell me about metallicity, Julie. And it's like, well, anything higher than everything that's lithium and above is considered a metal. The chemists get mad at us about that, but that's how we like it.
Yeah. Or when they talk about burning hydrogen, and I'm like, yeah, okay, well, great. We understand that means fusion. It doesn't actually mean that it's a fire. And that
Nothing's
one
on
really,
fire.
yeah, it's not on fire. Yeah, I think it's something when you give people astronomy education, you'll have all these things that you kind of know and you assume and you've picked up somewhere along the way. You're careful about how you're talking to them because
Yes.
it's like I said, when you get into these news items like this, um, people just kind of get lost or they don't realize what all goes into it. So,
Yeah,
but
it's amazing how simple a word can actually be lingo,
oh yeah.
right? Like burn, that's not a particularly scientific word. And yet,
And yet, oh yeah, it's like I said, whenever I do sort of astronomy stuff, it gets into the word day. Like you have a Martian day and you have an Earth day. But what is actually a day? Is it rotation on the axis? Is it sunrise to sunrise? You got to be careful about that one, right? And that's another one that even when I'm like teaching the solar system course that I do now, it's sort of like you got to remind them like sunrise to sunrise does not mean rotation on the axis. It doesn't actually even on Earth, but it's so close we can kind of fudge it. Um, but on somewhere like Mercury or Venus, it's like they're so totally disconnected. It's kind of fascinating, really. So, and I suspect a lot of confusion in science comes because we use terms, it's like you said, burn or something like that are just normal everyday words, and yet we mean them in such a different way. So,
yes, we do it to ourselves. which means that science communicators have
A big job to do.
a big job to do. Um, it's a fun job, though.
Yeah.
I enjoy it. All right. We've got 5 minutes.
Yeah,
Do
I
we
think,
want,
did you want me to just I can just cover that last little quick
let's do
meteorite
it.
one. Yeah, this was one actually Dr. Elena Hyde suggested to us, and I'd seen the story pop up somewhere and had sort of read it briefly. But of course, with all these, we've touched on meteors and meteorites earlier, but of the ones that hit the ground, there are always a few of them that actually originate on Mars. Right? So there's a fair number of Martian meteorites, and this is about one they found that turned up at Purdue University. There's a bit of a funny story behind that about it sort of spontaneously appeared in a drawer, and they're really not entirely sure where it came from originally. But what's really interesting is the team did some geochemical analysis, and what it comes down to is it strongly suggests this particular rock was exposed to water. Now, it's not a big surprise because the Spirit and Opportunity rovers back in the early 2000s had some fairly conclusive proof, geochemical proof again, that water had flowed on the surface. But it was interesting that now you're even getting Martian meteorites where you can find evidence of this. So it's you know it's quite interesting when you look at the rocks up close, and that this particular one is a meteorite that they figure got blasted off the surface of Mars around 11 million years ago, which meant it floated around for X, like however long before it finally hit Earth's atmosphere and ended up on the surface. We don't really know where because we don't know where it was picked up originally, but you can find out so much from the geochemistry of these kind of things. And in this particular one, they found that it was had been exposed to liquid water at some point in its past, because exposure to water does leave some fairly distinct geochemical record in the rock. So
Very cool. Um, it's it kind of tickles me that it was found in a drawer, and since they didn't know where it came from, and since meteorites are named after where they are found, it's now been called Lafayette, which is the town where Purdue University is. It's just like, whoop, it's the best we could do.
it's the best we could do. I mean, but it's interesting that like that this thing kind of shows up, and yet it still has so much to tell us
Oh yeah.
about the surface of another planet, because other than that, we still haven't actually sent any sample return missions to Mars at this point. Well, that's another one that they'll probably, is in the works at this point.
Yeah.
But
The samples are being taken. We
yeah,
just need to figure out how to get them back.
this Perseverance leaves its little trail of meteorites behind
Doop, doop,
it.
doop, doop, doop.
I've bagged them up and left them. You guys can figure out how to pick them up later. Um, I always get that impression when I think of that. It's like, okay, well, I've Ziploc bagged it and left it. You guys come and pick it up later. Um, which is a bit what geologists do as we're taking samples. We bag them and then, all right, leave them and then later come back and pick everything up and take it back to the lab. So one of those just odd thoughts that crosses through your head. But it really is amazing how much you can learn even from a relatively small rock sample, because this one is just like a hand size sample. And yet the techniques that we use, more of these indirect techniques, can really, really tell us quite a bit about the Martian surface, not just that it was underwater, but the processes that created the rock. A lot of the ones they find from Mars are igneous, not surprising, but there's quite a number of these around, which is how we know about some of the geology of Mars, even prior to the rovers ending up landing on the surface.
All right. Well, thank you for that. We are just about at the top of the hour. So, everyone, thank you for listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. Your hosts this evening have been Dr. Mary Helen Armour and myself, Jeannie Tomei. You can always connect with us on Instagram at the handle at YorkU Observatory and on Facebook at Allan I. Carswell Obs. Please check out our website, www.yorku.ca/science/observatory. Thanks for tuning in to York Universe, Clear Skies, and have a good night.